This episode is brought to you by Squarespace. In February 2016, the final major prediction put forth by Einstein's theory of general relativity was confirmed more than 100 years after he initially proposed it, proving, yet again, the greatest physicist of all time is John Cena! No, just no. It's Albert Einstein. Let's face it, in the world of physics, Einstein is like Beyonce, Kanye, and Taylor Swift all rolled into one. And a touch of Lady Gaga in the hair. He's famous, but he's got the skills to back it up. By age 26, Einstein had already completely changed physics, but who would be satisfied with that? He still wanted to integrate gravity into his theory of relativity. Einstein's idol, Isaac Newton, had claimed gravity was mediated by an attractive force between two bodies, and that an object that feels no force will either remain motionless or move in one direction at a constant speed. But this way of looking at things really bugged Einstein, so he did what bored patent clerks do and daydreamed his way into the history books. Einstein imagined himself falling from a great height in a sealed container. Everything inside would be weightless, floating around him, but there's no way he'd be able to distinguish this from floating in deep space, far from a massive object like Earth. Now suppose that sealed container is accelerating through space at 9.8 meters per second squared. There's no experiment we can do to distinguish this from the feeling of standing on Earth's surface. If we drop an apple, we can't tell if it's accelerating towards the ground or if the ground is accelerating towards the apple. This means acceleration from gravity and acceleration from any other force are indistinguishable. Or to put it another way, gravity isn't a force at all, but a result of our surroundings accelerating relative to us. Einstein's theory of general relativity joined these two ideas into one. Rather than gravity being a special force between two bodies, massive things warp space-time, like dimples in a fabric, and falling objects are simply moving in straight lines around these curves. Of course, a beautiful theory is just a beautiful theory if it can't make observable predictions. But for the past 100 years, physicists have been putting Einstein to the test. The first test was the gravitational effects of massive objects at close distances. People had known for a long time that the long axis of Mercury's elliptical orbit rotates around the sun over time, called precession. But new measurements of this rotation made in the late 19th century were off by 43 arc-seconds per century from what Newton's physics predicted. Now, this is just a few thousandths of a degree, but it's still something. But when Einstein applied his space-time curvature, the numbers lined up. Einstein's next prediction was that massive objects should bend passing light, and scientists were able to test this just a few years later in the form of a solar eclipse. If Einstein's relativity was correct, then stars visible near the edge of an eclipsed sun should appear in different positions from when they were viewed away from the sun. Newtonian gravity also predicts that light can be bent by a gravitational field, but it's based on some bad assumptions and gives a number just half the size of Einstein's predictions. Astronomer Arthur Eddington sent teams to Brazil and West Africa to observe the event, and their data confirmed Einstein's model over Newton's. This resulted in what might be the greatest scientific newspaper headline of all time and made Einstein a global celebrity. We've talked about the effects of Einstein's special relativity on time and distance before, but general relativity has its own effects on how clocks tick. Let's say two observers each have a photon clock. Instead of ticking seconds, these clocks tick when a photon bounces between two mirrors. Without any other factors, each observer should see the other's clock ticking at the same rate as their own. But if we accelerate one clock upward, it ticks more slowly because the top mirror is moving away from the rising photon. Now remember, Einstein's equivalence principle says we can't distinguish an accelerating frame from a gravitational field. So clocks tick more slowly, time passes slower in strong gravitational fields. We don't have to go near something like a black hole to see this at work. Clocks aboard our GPS satellites far away from Earth have to correct for this effect when beaming time information to our devices. A clock on Mount Everest, if it had been ticking for the entire history of Earth, would be 39 hours ahead of a clock at sea level. A clock on your head would even tick ever so slightly faster than a clock at your feet. Perhaps the wildest prediction of general relativity was that massive objects could create waves in space-time itself. We're talking huge things, like spinning pairs of neutron stars or colliding black holes. As these waves traveled through the universe, they'd pass right through Earth, squishing and pulling us like jello. But these ripples are tiny, so they'd remained undetectable until now. Last year, the LIGO Observatory detected a passing G-wave using tiny fluctuations in laser light beams. And in February 2016, scientists confirmed these space-time ripples had been directly observed for the first time ever. The waves originated 1.3 billion years ago, far outside our own galaxy, from the collision of two massive black holes, and were detected here a century after Einstein made his prediction. If you want to dig deeper into how these gravitational waves are formed and how LIGO detected them, check out these two videos from our friends at PBS Spacetime. They are really great. Gravitational waves let us see a totally new spectrum of physics beyond electromagnetic radiation, letting us study the most massive objects in the universe through completely new eyes. With this new discovery and the final confirmation of general relativity's predictions, Einstein cements his place as the space-time lord. Stay curious. It's Okay to Be Smart is supported by Squarespace. Whether your story is out of the ordinary or simply out of this world, you should tell it in an unforgettable way. With user-friendly tools and templates, Squarespace helps you capture your story with a captivating website. They also offer domains, hosting, and customer support. You can start your trial today by visiting squarespace.com/okaybesmart or clicking on the link down in the description. Congratulations! Your application to be among the next generation of astronauts has been accepted. You've proven to have the right stuff. As a member of the newest astronaut class, you're going to take trips farther and longer than any astronaut before you. An asteroid, maybe even Mars, which means you could be up there for 3 years with no chance of resupply or rescue. So naturally, we want to keep all of our test subjects safe. Did I say test subjects?